next talk is on preservation of speculative constant time by compilation. And Santiago.
Thank you for the intro. So today I will be presenting this work. My name is Santiago. This is work together with Gilles, Blatter, and Vincent, and Laporte. You can hear? Oh, okay. So I just look at you. This is work with my co-authors, and in this work we study speculation in the context of security. We show that a proof of concept compiler that we mechanize in COC preserves. Okay. Close. Maybe in the flap. 1, 2, 1, 2. Okay. Okay, that sounds better. We study speculation in the context of security, and we show that a proof of concept compiler preserves non-interference even under speculative semantics. Okay. I'll try louder then. So I will begin with the 3 main takeaways of this talk, which are that we model speculation with directives in a verification-friendly way. We want to model predictions from the CPU with respect to branches. So if the CPU predicts that a branch will be taken and is actually taken, we represent this with a step directive. And when the prediction goes wrong for a particular branch, or an adversary mistrains the predictor to get the wrong branch, we represent that with a force directive. Then execution is indexed by a list of such directives that guide execution. Second main takeaway, the interaction between speculation and different compiler transformations. We use transformers for directives and observations to establish the usual simulation diagram to prove preservation. And lastly, we show that a proof of concept compiler with 9 simplified but representative passes preserves the security properties. I will recap the basic example of Spectre v1 that we saw in the previous talk. Maybe I can use this. Okay, I'll try this. Testing. Okay, that's better. So I will quickly recap the example for Spectre v1. Remember, this is conditional branch speculation that we saw in the previous talk. I'll be quick because of that. So I have 2 arrays that are on my stack, A and B. They contain secret and public data respectively. And my program compares an index I with the size of B, performs a load at this position, and then branches on the loaded value. This, as we saw in the previous talk, is dangerous because even though B contains public data and then branching on Y is okay, this, which means that this program is what cryptographers call constant time, that the time that it takes to execute this program is independent from secrets. Under a speculative semantics, this program is no longer secure. The processor might speculate on this branch and execute the access even when the index is out of bounds. When the index is out of bounds, the address can point somewhere else outside B, for instance A, where my secrets are. And Spectre attacks exploit the fact that when the processor rolls back speculation, it doesn't roll back the microarchitectural states such as the cache. So then we can do cache attacks on misspeculated executions. Therefore, we say that this program is not speculative constant time. It's not constant time under speculation. Our goal for this work is to take programs that are secure against Spectre for different kinds of mitigations, and to show that our compiler preserves this property, preserves safety against Spectre. This is not so trivial. It's easy to find examples where mainstream C compilers either remove mitigations that we inserted against Spectre or introduce new vulnerabilities to our programs. But perhaps more interestingly is that our compiler that is security-oriented, which is called Jasmin, we informally conjectured that it preserved the mitigations, that it didn't introduce vulnerabilities, but when we were proving our proof of concept compiler, we realized that one of the passes introduces a vulnerability when sharing memory between different arrays if they are secret and public. Luckily, after the fix, all our Jasmin development was still secure. Okay, so to reason about preservation, we need to have a semantics. It's very similar to the previous talk. I will give a quick recap. So we have a semantic like this, where S, which is a state, steps to a state S prime and produces an observation O. The observation is what the attacker can measure about your execution. We have three kinds of observations in our work. For memory accesses, such as loads and stores, we have addresses. So here I'm accessing array A at position E, and I'm leaking the address A with the base pointer and the evaluation of E, that is the index inside the array. Then for conditionals and loops, we have that we leak the evaluation of the condition, E in this case. For other instructions that do not vary their time through their data, we have a dummy observation bullet. In this framework, being constant time is that O, which is above the arrow, is independent from secrets. Now, to take Spectre into consideration, this is where we differ a little bit from the previous work. We introduce directives to this statement. So D, below the arrow, it guides the execution. It represents the prediction from the CPU. For instructions that do not need any prediction, such as loads or stores, we have a step directive, which is the usual step that you perform sequentially. Note that we leak the same as before. Now for conditionals, this is interesting. For loops, it's the same because they're both branches. We have a force B directive. B is a Boolean that determines the branch that gets executed. We leak the same as before, the evaluation of the condition, but the branch that gets executed depends solely on this directive that is adversarially chosen. The last directive that we have is for out-of-bounds accesses, which are very common in misspeculated execution. This depends on an out-of-bounds access can access different parts of memory at different points in time, depending on how the compiler lays out your stack. And therefore, we allow the adversary to pick B and I, an array and an index, to access an arbitrary address of their choice. Then with these definitions, speculative constant time, this definition is a little different from the previous talk. We say that a program is speculative constant time if for any prediction behavior D, the observable effect, that is O, is independent from secrets. Okay, now moving forward to preservation, we rely on previous work on preserving constant time, where we establish the usual simulation diagram. We want that if our source is constant time, leaks no secrets, our compilation is constant time, leaks no secrets. And we have the standard diagram where a target state T steps to T prime. We want that S in relation steps to S prime and is still in relation. The key to preserving constant time is to relate the observations, OS and OT. We relate them with a function, a transformer for the observation, that explains target observations in terms of source observations. The intuition being that if OS, the source observation, contains no secrets, then a function of it, which is the target observation, contains no secrets either. To introduce speculation into the picture, we need to account for the directive that the target follows. So the target performs a step under a certain prediction, and we need to find out what prediction the source needs to perform the step that we want. For this, we introduce another transformer, a directive transformer, that guides the source speculation in terms of the target behavior. This is the essence of our approach. So directive and observation transformers to establish the simulation diagram. The general statement for our theorems is as follows. We have a source and target programs S and T. We have a pair of inputs, I1 and I2, that coincide in their public part. They are indistinguishable. And we have a target execution starting from I1 under some predictions D. We want to find a source execution guided by G, the directed transformer, that explains via F, the observation transformer, the observations that we saw at the target. The generality, with respect to the previous slide, comes from the transformers taking the whole trace of execution, so all the directives up until now, and the other input. So the transformers can look into the public part of the input, not the secret part. An interesting point is that this approach of establishing transformers for the simulation is complete in the sense that if the pass preserves speculative constant time, then functions exist. The precise statement is as follows. Let's say that we have our source that is speculative constant time, and then these three statements are equivalent. Our compilation is constant time, there is a simulation with transformers, as I discussed, or there is a simulation cube. A simulation cube is the natural extension of how previous work used to deal with constant time. We illustrate our approach with the proof of concept compiler that we mechanize and prove in COC. Our compiler has 9 passes, such as constant folding, dead branch elimination, array reuse, and RTL generation. In this talk, I will discuss 2 of them. Constant propagation tracks the value of variables and replaces their uses by their values. So in here, we have x that receives 3, and then it can replace the use of x inside the load by the value 3. If we are careful with our analysis, this pass preserves constant time, speculative constant time, because the intuition being that the access to A at position x plus 4 leaks the same as the access to A at position 3 plus 4, which is A7. We need to be careful with the analysis because when we track the value of x, we cannot assume the branches go the way we expect them to. We need to over-approximate branches in a sound way with respect to speculation. To establish the simulation diagram, for this case, is very easy. We pick the transformers, F and G, to be the identity. This means that the programs are in lockstep, and every target step can be replayed exactly by the source. Expressions evaluate to the same values, and thus observations match exactly. Now, a little bit more interesting is data assignment elimination. So in this program, we have x that receives 3, then the result receives x plus 4, and then we overwrite the result with receiving 2. Then this pass will remove the first 2 assignments because they don't contribute to the final result. And again, if we are careful with our liveness analysis, this pass preserves speculative constant time, the intuition being that dead variables don't contribute to the leakage, otherwise they wouldn't be dead. The simulation diagram is a little more interesting because the source needs several steps to catch up with the target. So we have a target step, and now the directive for the transformer for directives needs to take the target directive, which is the useful step, and introduce a prefix of step directives that execute the dead assignment. In our case, it's just 2. Then the observation transformer takes the source observations. It needs to recognize and remove the prefix of dummy observations from the dead assignments and return the final observation, which is the useful one. So now I will summarize by revisiting the takeaways. We use directives to manage non-determinism and to consider one trace at a time. We can define transformers very conveniently using directives, which help us when proving hyperproperties. We can establish a simulation square instead of a simulation cube, which makes things easier. And transformers characterize a compiler transformation in terms of its effect on speculation and on leakage. And finally, we show that several compiler passes can preserve speculative constant time. We mechanize this in COC, which you can check out together with the paper at this link. Thank you very much.
Any questions, please?
This? Okay, it sounds working. Thank you. So thanks for the great talk. So my question is that you basically focus on the cache or time inside channel, right? So just wondering, like, could you elaborate a little bit more about how register allocation would impact this speculative information leak or not?
Can I do? Okay. It's so register allocation has we consider a kind of register allocation in our work. We split the pass in two concerns. First, you decide what you want to spill such that you have enough registers, and then you decide which variable goes in which register. The second case is what we consider in our work, and this is checking alpha conversion between two programs. The programs are the same, so this is perfectly fine. The first part is difficult and it does not preserve speculative constant time because it introduces new chances for vulnerabilities. And you will hear all about that in the next talk, which Soren will show us how to fix register allocation such that it preserves speculative constant time.
Anybody else? Let me ask a question too. So if you, over here, so you showed the case where you do, you remove this axis to X in the middle. What if that axis that you remove has a memory axis inside, or not?
Yes, that's a good question. So here I was assuming that X was in a register, but we allow, in our framework, we allow removing such accesses if they're really dead. Then this produces fewer chances for mispeculation, and this is fine. In general, again, this is in a context where you have to analyze the program and decide which ones really don't contribute. But yes, this is allowed.